So hello everybody, welcome to this session, masterclass session on Frontiers course. Today our speaker is Dr. Niall Holmes, and he actually started his career here at the University of Nottingham, where he did his undergraduate degree. Since then, he's done his PhD at Nottingham under the supervision of Professor Botal and Professor Brooks, where he was doing cutting-edge research using new technology and developing that new technology to look at how the brain works. So he's been developing the technology, and that has resulted in a really high profile paper that was published in a journal called Nature, which is one of the most prestigious journals there is, and he achieved that all during his PhD. He now works still at the University of Nottingham in the Sir Peter Mansfield Imaging Centre, furthering the development of the technology that he's been working on.
Yeah, my talk's called Quantum Sensing the Brain. Just a bit of overview. I'll talk a little bit about functional brain imaging. I'll then talk more specifically about a technique called magnetoencephalography, or MEG. I'll then talk about the technology that we've been able to harness in order to develop a new way of scanning the brain called an optically pumped magnetometer. I'll then discuss OPM MEG, so combining OPMs with the MEG, and then a bit of an overview of the system and challenges faced as we developed it, and then just some example results, future directions, and sort of conclusions. So I'll just skip over that and move on to functional brain imaging. So the human brain has 100 billion neurons. Each neuron is connected to 10,000 other neurons, and sitting on your shoulders is the most complicated object in the known universe. And it really does just highlight that actually understanding the human brain and treating brain disorders is actually one of the biggest challenges for 21st century science. Neuroscience in general has been revolutionized by our ability to image non-invasively brain structure and brain function. But we still know relatively little about how healthy brain function is mediated, and also just the neural substrates that underlie serious mental health conditions. We know even less about the development of the brain, so from childhood to adulthood, and that's mostly because of the scanning technology that's available. So if we look at the typical technologies, we might think about X-ray CT or MRI, so pictures of the brain, but actually in many brain disorders, they look relatively normal. If we compare a nominally healthy person to a person with a brain disorder, the actual structure looks the same. What's going on is that the underlying neurophysiology is what's breaking down, and for that we need to look at brain function. So we can do functional MRI, which is a technique that was sort of pioneered here at Nottingham, and it measures brain function via changes in metabolism. So as the neurons fire and use energy, they need to replace that energy by bringing in more oxygenated blood. This means it has poor temporal resolution because it's not a direct measure of the brain physiology. We can also do a similar thing with positron emission tomography, or PET, but that requires the use of ionizing radiation. Electroencephalography is what's more commonly used to assess brain function, but it has low sensitivity and a very poor spatial resolution. And that's mostly due to the conductivity of the scalp. So that brings me on to MEG. So magnetoencephalography is where we measure the magnetic fields that are generated by neuronal current flows. So much like the passing of an electrical current down a wire that generates a magnetic field, the passing of electrical currents down neurons in the brain generate magnetic fields. We take the magnetic fields measured on the scalp. We then do some source localization. So this is where we convert the magnetic fields into an inferred neuronal current. This source localization is a very complex process. It's called a ill-posed inverse problem because there are essentially infinite solutions to any one magnetic field. Could be constructed by an infinite number of electric currents in the brain. So MEG is a large technical challenge. The magnetic fields generated by the brain are on the order of femtotesla, so that's 10 to the minus 15 Tesla. That's about 1 billion times smaller than the Earth's magnetic field. Measurement of the MEG signal is like finding a needle in a haystack, or measuring the footprints of an ant at a rock concert. So we really are trying to do a very complicated thing, and To attenuate these external interference sources, we tend to store our systems in magnetically shielded rooms. So these rooms are made of a material with a high magnetic permeability, and that means that when magnetic fields impact on the room, the flux gets diverted around the room instead of through it. So inside the room, we go from a field of about 60 microtesla to less than 20 nanotesla, and sometimes down to 1 or 2 nanotesla. The sensors that we use to detect these femtotesla level changes in magnetic field are called superconducting quantum interference devices, or SQUIDs, and they're sensitive to changes in magnetic field of around 3 femtotesla. We tend to put around 300 of these SQUIDs inside a dewar of liquid helium, so the liquid helium brings them down to superconducting temperatures, which allows them to operate. So this is what a MEG scanner looks like. This is the one at the University of Nottingham. MEG is has had a big impact on neuroscience. It's a very useful technology, and it's told us a lot about the brain. But the cryogenic cooling involved means that the sensors are a long way from the head. So if you think about it, they have to be fixed in place with the insulation gap so that we don't freeze the heads of our participants. This reduces the signal to noise ratio as the magnetic fields from the brain fall off with R². They're also one-size-fits-all helmets, so the brain sensor distance is even larger in adults, which means that scanning babies or children is challenging, just because we can't have enough signal. Because the sensors are fixed in position, it means any movement relative to the sensor array degrades data quality, and that means it's very hard to scan people that move. So also the available technologies to stimulate the brain is changing, so virtual reality is being employed in more and more areas. It could allow us to generate immersive environments, but that requires head movements. MEG scanners are also expensive to buy and maintain. I think liquid helium's something like in the region of like £10 a litre, and we pump 100 litres into our system every week and have been doing so for 10 years. So you can imagine the bill that's running up. All of this leads to us to want to change it, so move from a system that's bulky, expensive and inflexible to something that you can wear like a hat and just move around, interact with the world as you normally would, but we can scan your brain at the same time. But until now, we've not been able to make that jump. The SQUID technology is just so restricted to the dewar that we needed something else to get us there. So this brings us on to optically pumped magnetometers. The recent advances in quantum technologies and in miniaturization of complex systems has seen the development of these compact optically pumped magnetometers. So OPMs have a performance similar to that of SQUIDs, but don't require cryogenic cooling. This means they could be the building blocks of a wearable MEG system. OPMs use laser light in order to measure changes in magnetic fields experienced by atoms. These OPMs are being made by a company in Colorado called QSpin. So they've developed the first commercially available fully integrated OPMs with a sensor size and sensitivity that's suitable for OPM MEGs. We've been working quite closely with QSpin since they've started developing these sensors, and we were actually lucky enough to go and visit them back in 2018. So we've been able to work together to inform what works from the scanning side of things, what works from the physics side of things. How can we make the experience in the system as good as possible? There is a problem though. So plus or minus 1.5 nanotesla is a really narrow range over which we can do our experiments. And although I said we've got these magnetically shielded rooms, there is still a movement problem. So OPMs are vector magnetometers. They measure the field along a sensitive axis. So in this case, they measure the field along what we call their radial axis down here. This means what they actually measure is the dot product of the local magnetic field with their orientation. The narrow dynamic range means that small movements inside the MSR, where we have a non-spatially homogeneous field, means that even small movements like 1 degree, a couple of centimeters, can take us outside our plus or minus 1.5 nanotesla range, and that would just completely saturate our signal. It means we need to null this remnant magnetic field inside the MSR and flatten it out, and then that will allow us to move more easily. We can use electromagnetic coils to do this, so we can use them to generate magnetic fields which are equal and opposite to those in the room. And I spent most of my PhD work designing these biplanar coils, which are placed either side of the subject that allows easy access in and out. And they have wire paths that make uniform fields and spatial field gradients. The designs themselves are adapted from MRI gradient coil design methods, And actually Sir Peter Mansfield's work in this area at Nottingham contributed to him being awarded the Nobel Prize in 2003. So it's good to see technologies being created and being reused. Now that we've created our nice field environment and we've got our OPM sensors, it's time to do some neuroscience and actually see if we can exploit the potential of these sensors. She was asked to bounce a ping pong ball on a bat, and we recorded the brain data, and you can see here she bounces the ball, and in the brain, in the motor cortex, we get this decrease in blue while she bounces the ball. So she's still moving her hands, so we've got motor activity. And then when she stops, we get this red rebound as it returns to baseline. So it shows that we can actually measure, with high spatial resolution, high temporal resolution, high quality signals during these large movements. You could not do this in an MRI scanner. You could not do this in an X-ray machine. You couldn't do this in a normal MEG scanner. And if you did this in an EEG system, what you generate would be quite a lot of muscle artifacts that would distort and ruin the data. We can also look at different ways of stimulating the brain. So a lot of brain experiments are quite boring. You get in a scanner, they tell you to look at a cross and press a button when you see a face instead of a house or something like that. And you sit there for an hour and you keep pressing these buttons and then you fall asleep and then you ruin their experiment and then they're not very happy with you at the end. But what we can do is combine virtual reality headsets like an Oculus Rift to create an immersive environment that just show us what the brain's actually doing in our day-to-day lives. So these systems have, they have sort of two screens. They combine the vision, so you get a 3D effect, and we can wear that over our OPM systems to, isolate visual stimuli. So that was our sort of initial experiments. We had an array of OPMs, about 30 OPMs. So we weren't able to put them all the way over the head. We were able to isolate different brain regions for targeted experiments. But actually, what's probably more important in neuroscience and in development is looking at whole head activity. So there were some developments that were required for that. So first up, we worked with QSpin quite closely to shrink the size of their sensors from something about this size to something that's more like a Lego brick or a couple of Lego bricks put together. We then worked with a company in Nottingham called Added Scientific, who specialise in additive manufacturing, so like clever 3D printing. We developed a new helmet with them, which allowed us to put sensors all over the head wherever we wanted to. It's also generic, so it can go on anybody, and we can figure out where the signals came from. And that's a photo of it in action. It's been pointed out that it looks a lot like Toad from Super Mario. So some of the early whole head results were to compare the OPM MEG to a state-of-the-art squid system. You have the motor region of the brain is activated during a finger movement, and so this is visual gamma being induced in the brain. If we compare that to the same results in the squid system, we can see in the same subject we get really good repeatability. So we got high repeatability, and it means that our 50-channel system is performing as well as a 275-channel cryogenic system. And that's all because we're measuring closer to the head, so we're able to access higher signals, higher spatial frequencies, and do a much better job than we'd be able to with the squid system. This allows us to do some more exciting experiments, so opening it up to sort of, real neuroscience. So one main thing in neuroscience is connectivity. So if you think about it, the brain regions don't work in isolation. If you see a football, a part of your brain the visual cortex has to speak to your motor regions in order to say kick that football. So there's information flow through your brain, and actually we're able to visualize this by measuring the activity in real time. So if you think about it, also it means that your left and your right motor regions should probably be connected to each other, because what you do with your left hand might inform what you're doing with your right hand. So an information transfer makes sense. So if we look at the time course of electrical activity in one side of the motor cortex, compare that with the time course of activity in the other side, we can see they're actually going to be pretty similar. And if we make maps of these correlations between time courses at different parts of the brain, we can investigate healthy brain function, but we can also investigate dysfunction, so in brain disorders. And we've very recently actually shown that the OPM MEG system we built identifies the same networks as a cryogenic system. So this is sort of motor connectivity that's shown in the same subject in cryogenic and OPM MEG, same for the other subjects. So this is really exciting and means that we're doing complex analysis of unaveraged data. So we're not doing multiple trials to boost it. We have to just listen to what the brain's doing at rest investigate that. So it means our system's working really well with high signal to noise ratio. There's also obviously loads more applications that we could use, and it just shows you the power of the technology, and that the group have gone from simulation studies in 2016 all the way through to where we are now with the 50 channel recordings. So just to wrap up, I guess the OPM MEG has seen a rapid development, has a very promising future. This is a massive project. This has been led mostly by Matt Brooks at the University of Nottingham, and then everybody else listed here. We've worked in close collaboration with UCL to develop the first systems. Added Scientific obviously built our helmets, Q-Spin to build the sensors themselves. The University of Oxford are helping us with motor learning, but also with the paediatric study. This has been a lot of funding organisations involved, and I'm very lucky to be a part of the project. I'm very thankful for working with some great people. So yeah, thank you all for listening, and I hope you enjoyed it.